Hello. Today we are going to discuss classifying angle pairs when a transversal cuts lines. A transversal, a line that cuts two other lines, so in my diagram this is that diagonal line, here is my transversal. It cuts two different lines. When we have a transversal cutting lines, we classify angle pairs. Pairs of angles in this upper area and this lower area to relate them so that we can make mathematical conclusions about them. The four types of angle pairs that we use specifically are what are referred to as corresponding angles, alternate interior angles, alternate exterior angles, and same side interior angles. Now, what we must realize first of all is that, remember, we are very boring in the world of mathematics, and nomenclature is very straightforward. When we talk about angle pairs, we are referring to the location of two different angles with respect to, one, their location with respect to the transversal, and two, their location with respect to whether they are inside or outside of the two lines that have been cut. For example, same side interior angles. Well, those are two angles that are on the same side of the transversal and on the interior of the two lines that have been cut. Very straightforward. An example of same side interior angles would be angles 3 and 5. As I overlay here, we can see that the two angles are on the same side of the transversal and inside of the two lines that have been cut. Same side interior angles. Quite obvious. On a similar vein, alternate exterior angles, well, alternate means they are on different sides of the transversal, and exterior means they are outside of the two lines that have been cut. Angles 2 and 7 are clearly on different sides of the transversal and outside of the two lines. Alternate exterior angles. I think we're getting the hang of this now. So it's probably no surprise that alternate interior angles are on opposite sides of the transversal and inside of the two lines that have been cut. The two green angles represented here show as much. The only one that is not as ridiculously obvious in its description are corresponding angles, yet they still make very perfect sense in that they are referencing angles that open in a corresponding direction. Angles 2 and 6 open in the same direction. They are both in the upper right-hand corner with respect to the transversal and the lines they have cut. On a similar vein, angles 1 and 5 are corresponding. Angles 3 and 7 and 4 and 8 are corresponding angles. An easy way to kind of think of this is to relate it to a coordinate plane, in that if the angles you are associating would be in the same quadrant, first quadrant, second quadrant, third quadrant, fourth quadrant, first quadrant, second quadrant, third quadrant, fourth quadrant, 2 and 6 would be in that same quadrant. Those angles would be corresponding. Very easy, straightforward naming in math. However, one of the things that we did want to discuss is making relationships to those angles measures. And here's how we're going to do that. I have a triangle here. A very simple triangle. Has no special characteristics with respect to the angles. But I've colored each angle to show the three so they would stand out. And what I have done is I am going to take this triangle, rotate it, and translate it several different ways so that I can create a pattern, a tessellation, as so. You will notice, as I overlay, the same triangle has been rotated and translated several times to create the pattern. Now, what is very unique about this is that through a variety of translations and rotations, each of these lines are in fact parallel. There are many different ways to prove this. Distances being the same because it is the same triangle are the easiest ways to prove as such. The reason having parallel lines is important is because when lines are parallel, the relationships of our angle pairs can allow us to make conclusions about their measurements. An easy way to look at this. Let us start with corresponding angles, which for us were angles 2 and 6. Corresponding angles, as you can see, have the same color. It is that same angle of that same triangle, even though it's been rotated or translated several times. Corresponding angles are both green in color. That tells me that when lines are parallel, corresponding angles are congruent. To a similar vein, alternate interior angles. Through a series of rotations and translations, we see that they are also an angle that is the same color. It is the same corner, the same angle of that triangle. A very easy visual proof as to why alternate interior angles are also congruent. Alternate exterior angles. Again, both green in color. Through a series of rotations and translations, it is the same angle of a triangle. When lines are parallel, alternate exterior angles are also congruent. What about same side interior angles? Well, here I actually have something slightly different. Same side interior angles. Hold on. We initially represented them as so. However, you can tell that even though I represented them as so, those angles down here aren't also green in color. They are in fact red and blue. Same side interior angles are green, red, and blue. And if I bring my triangle back, it shows that same side interior angles are actually combining to be the three angles of a triangle. Well, as we have a solid foundation and knowledge of the triangle sum theorem, we know that the three angles of a triangle add to 180 degrees. Well, if same side interior angles are made up of the three angles of a triangle, that would lead us to the conclusion that same side interior angles add to 180 degrees. Fairly simple. Corresponding angles, when lines are parallel, are congruent. Alternate interior angles, when lines are parallel, are congruent. Alternate exterior angles, when lines are parallel, are congruent. Same side interior angles, when lines are parallel, add to 180. Now, before I go, one brief thing with regards to all of these as I remove the tessellation. One thing you might note when it comes to angle pairs, specifically, of course, again, when a transversal cuts parallel lines, is that there are really only two possible mathematical measurements that we can associate with them. They are either congruent or they add to 180 degrees. So here's a brief little tip. Since there are only two things that can happen, they are either congruent or add to 180 degrees, I give you this bit of advice. If angles look like they are the same, again, assuming lines are parallel, they're going to be the same. If angles look like they're different, well then, they're likely going to add to 180 degrees. Thank you.